So we're going to finish off the class by finishing off maximization and minimization problems. Last time, when we talked about those, we talked about critical points. Critical points are places where the function might take a maximum or a minimum. We can detect them by checking when all the derivatives of the function are equal to 0, meaning the x derivative, the y derivative, and the z derivative are 0. And then we have a second derivative test. That can tell us whether we have an actual legitimate local maximum or local minimum. But if we want to find the global maximum or minimum, the absolute biggest and the absolute function, absolute smallest that the function can get, we also have to check the boundary of that region. And surprisingly, in one-dimensional problems, this wasn't hard. We had a region which was usually like an interval, x goes between 0 and 5. So we just had to check x equals 0 and x equals 5. But in 2 dimensions or 3 dimensions, this actually becomes a bit more of a big deal, because when we were talking about regions in the real line, the boundary of a one-dimensional region is just some points. It's 0-dimensional. But the boundary of a 2-dimensional region, like we see in the lower left here, is a whole one-dimensional region by itself. And so if we want to look for maxima and minima on the boundary, we then have to check a one-dimensional region. And so here's the general procedure for finding the maximum or minimum on the boundary. So to look for the max or min on the boundary, we kind of have to parameterize the boundary. Then we plug our parameterization into the function, and we look for critical points the same way as before, and then we have to check the boundary of this parameterization. And this means that we have a recursive procedure. If we've got a 2-dimensional maximum or minimization problem, first we look for critical points on the inside. Then we parameterize the boundary. That's a one-dimensional maximization minimization problem. And then we check kind of the boundary of our parameterization. That's a 0-dimensional maximization minimization problem. For a 3-dimensional region, we first check for critical points on the inside. Then we parameterize the boundary and do a 2-dimensional maximization minimization problem, which means, again, we may have to do a 1-dimensional maximization minimization problem to do the boundary of the boundary. So this is definitely more work than it used to be in single variable calculus. And so we got to be a little bit careful about this when we're actually checking these things.